it hits you every day, right? This just overwhelming flood of information.
Oh, yeah.
Trying to make sense of it all, to really know what's going on, feels like, I don't know, a constant uphill battle sometimes.
It really does.
And that's precisely why we do what we do here at the Deep Dive. We're your shortcut, your expert companions cutting through the noise to deliver the crucial insights, the unexpected angles, the stuff that truly matters, all custom built for you, the learner.
And today, well, we're venturing into some really quite groundbreaking ideas, I think. We've got this detailed set of notes from May 26th, 2025, that lay out a fascinating, really intricate system for how future AI could fundamentally structure its understanding of the world.
Okay.
Forget simple lists of facts. This is more about a deeply organized internal architecture. The notes actually call it the Conceptual Onion for advanced language model.
A conceptual onion. Okay, right off the bat, that sounds like something with layers. Layers of understanding, maybe?
Exactly. That's the core idea. Think of it as AI knowledge organized not linearly, but in a nested, interconnected way. It's designed for maximum efficiency and, well, insight.
Okay.
And at the heart of this whole framework, the notes point to this fundamental principle called Recursive Abstraction and Refinement, or RARF. That's sort of the engine that builds and maintains this layered structure.
Recursive Abstraction and Refinement, RARF. Okay, let's break that down. Abstraction, that sounds like going from specific details to the bigger picture.
Yeah, the general idea.
And refinement, well, that implies constant improvement, getting better. But what about recursive? What does that part mean here?
Right, the recursive bit means this whole process, abstracting and refining it, happens again and again at every single level of this conceptual onion.
Oh, okay.
It's a cycle where each level kind of builds upon the previous one. It identifies the core elements, understands their relationships, spots the limitations or the fuzzy areas. And then it uses those limitations to create a more abstract, more comprehensive understanding at the next level up.
Okay, so it's like this constant upward spiral of understanding with each layer learning from the one below it. That makes sense. So let's dive into this onion. What's the very first layer, the foundation?
So the innermost layer, they call it level 0, is termed primitives.
Primitives.
Yeah, these are the absolute most basic building blocks of meaning for the AI. You can think of them as the fundamental units of language understanding, maybe like individual word embeddings, that kind of thing.
Okay, like the atoms of meaning.
Exactly. Now, the notes get a bit technical here. They mention that mathematically, these are represented as vectors in what are called abelian or vector spaces.
Vector spaces.
What?
Right. That still sounds a bit abstract, maybe.
Yeah.
Can you give us a more intuitive picture of what that means?
Sure. Imagine you're plotting words on a map, right? Where the position of each word reflects its meaning. That's basically a vector space. Words with similar meanings. They'll be located closer together on this map. And what's really powerful is that you can do math on these word vectors. For instance, you can take the vector for king, add it to the vector for woman, and kind of surprisingly, you might end up really close to the vector for queen.
Huh, interesting.
Computationally, these primitives are the fundamental data units tensors that are already used in current AI systems like, PyTorch and TensorFlow. The conceptual onion basically takes these existing powerful representations as its starting point.
That makes sense.
Yeah.
So these word meaning vectors, these tensors, they're the seeds. What happens when we move out to the next layer, level +1?
Right. Level +1 is where these basic meaning units start to combine into more complex concepts and relations.
Okay.
The notes suggest that these are represented using mathematical structures called hypergraphs or simplicial complexes.
Hypergraphs and simplicial complexes.
Okay.
That sounds like we're moving beyond just simple one-to-one connections between things.
Precisely. A regular graph, just shows connections between pairs of items. A hypergraph is more flexible. A single hyperedge can connect multiple nodes all at once.
Huh.
Think of it like a group of words all contributing to a single, more complex idea or concept. It captures richer, sort of multi-way relationships that simple pairwise links might miss.
Gotcha.
And simplicial complexes are similar in spirit. They allow for relationships of different dimensions, individual concepts, connections between pairs, groups of 3 forming a higher level idea, and, well, so on.
Okay, so level 0 is the individual meaning components, the vectors. Level +1 is how they group into basic ideas and how those ideas relate. using these hypergraphs. What about level +2? How are these initial concepts organized?
So level +2 deals with frameworks and composition. This is where the notes introduce the idea of using monads.
Monads. I've heard that term from functional programming.
Exactly. It's a concept from advanced math and computer science. Here, it's used to structure how these basic concepts are sequenced and combined into more complex methodologies or procedures.
Okay, so monads bring a kind of order to the process. But what do they actually do in this context? How do they help?
Well, think of a monad as a way to manage computations that have some kind of context or dependency. Imagine you're building with Legos, right?
Uh-huh.
And some Legos have special properties. Maybe they need specific steps before you can attach them. A monad provides a structured way to handle these special cases, these contexts, and ensure everything fits together logically.
Okay, like a container for the process.
Sort of, yeah. The bind operation within a monad is key here. It lets you chain operations together while being aware of this underlying context. It helps prevent errors and ensures a coherent flow, especially in complex reasoning chains. The notes even draw parallels to established software design patterns, reliable ways of structuring code to handle complexity.
Right, so it's not just about having the concepts, but having a reliable, structured way to put them together to form more complex understanding, like a recipe. Where does that take us in our onion, level +3?
Level +3 introduces something called Schwann, which the notes define as strategy and context.
Schwann.
This layer is all about how the frameworks and methodologies we just talked about, the ones built with monads, how they're actually applied to specific goals and within particular situations. It's where the idea of a strategic space comes into play.
A strategic space. So it's about taking those general tools, those frameworks, and adapting them for a specific purpose or problem.
Exactly that. It's tailoring the general frameworks to achieve particular objectives, really taking into account the specific environment and the requirements of the situation.
Okay, makes sense. And we continue outwards. What's the focus of level +4?
Level +4 is called ZIMP, and it focuses on teleology and systemics.
Teleology.
Sure.
Okay.
Right. This layer is concerned with the functional role, the purpose of the strategies developed at level +3, but within a larger system. It's about understanding the why and the impact of these goal-oriented actions within the broader environment they operate in.
So it's not just having a plan, but understanding its place and purpose within the bigger picture.
Interesting. And what about level +5, getting towards the outer layers now?
Level +5 is PXAI. The notes say this stands for axiology and epistemology.
Whoa, okay. Axiology values, epistemology knowledge.
Exactly. This is a really fascinating layer. It deals with defining the core values that guide the AI, the criteria for what it considers valid knowledge, and the fundamental principles that govern its reasoning. It's like its internal philosophy almost.
Right.
And the notes specifically link this level to something called the conceptual loss function, which is crucial for the learning process. We should definitely circle back to that.
Yeah, absolutely. Values and knowledge validity. This sounds like the core ethical and, philosophical framework for the AI's entire understanding. And finally, the outermost layer, level +6.
Level +6 is simply called GU, described as transcendence.
Yeah, it's presented as the ultimate all-encompassing context, the broadest possible frame of reference that the AI can potentially consider, the absolute biggest picture.
Wow. That's quite a journey, isn't it? From the basic building blocks of meaning, these primitives, all the way out to universal context with GU. So how does this entire conceptual onion actually learn? How does it adapt and become more sophisticated? What's the mechanism for its growth?
Good question. That's where the concept of Hyper-Topological Monadic Optimization, or HTMO, comes into play.
HTMO. Okay, that's a mouthful.
It is, but the notes describe this as the overarching meta-algorithm, the main learning process that drives the refinement and evolution of the entire conceptual onion structure.
Okay, HTMO. It sounds like a very sophisticated learning process. What's the core idea behind it? How does it work, basically?
Well, at its heart, HTMO operates through a continuous cycle of essentially trial and error, but it's guided by something called a conceptual loss function.
The thing linked to level +5.
Exactly. It constantly makes small adjustments, small tweaks to the conceptual onion, maybe adding a connection, maybe refining a concept, and then it evaluates how those changes affect its overall performance, always aiming to minimize this loss over time, getting better and better.
Okay, and what exactly does this conceptual loss measure? What is the AI actually trying to get better at? What defines better?
Right. The conceptual loss isn't just one thing. It's made up of several components working together. There's a reconstruction loss, for instance.
Yeah.
This measures how accurately the AI can reconstruct lower-level concepts from the higher-level abstractions it's formed. Think of it as testing whether the AI can reliably unpack a complex idea back into its fundamental components without losing information.
So checking its own compression, kind of.
Yeah, in a way. Then there's also a predictive loss. This assesses how well the conceptual onion actually helps the AI perform on specific external tasks. Basically, does this structured knowledge lead to better predictions or decisions in the real world?
Okay, so it's about both internal coherence, can it unpack its own ideas, and external usefulness, does it help it do things better? What else contributes to this loss?
Well, there's a compression efficiency component. This encourages the AI to represent knowledge in a concise, elegant, and meaningful way. It penalizes overly complex or redundant representations.
Not really.
Tidy thinking.
Kind of, yeah. Then there's topological regularization. This uses ideas from a field of math called topology
Topology again.
to ensure that the AI's understanding is structurally sound, that it doesn't have weird, illogical gaps or inconsistencies. Think of it like making sure the connections between ideas form a coherent, well-connected shape, not just a jumbled mess.
Makes sense.
And finally, there's a coherence loss, which specifically looks for and penalizes any contradictory information within the AI's knowledge base. It tries to maintain internal consistency. So it's this constant balancing act.
Yeah.
Compressing information, being useful, staying logically consistent, keeping things organized internally. How does HTMO actually figure out how to make these adjustments? It can't just use the standard learning methods like backpropagation that we see in most AI today, can it? That seems too simple for this structure.
That's a key point. You're right. The notes explain that HTMO estimates what they call a conceptual gradient, basically, the direction of improvement, but it does it through a process of making small changes, perturbations, to the conceptual onion and then seeing how those changes impact the overall conceptual loss.
Wow.
So instead of directly calculating the mathematically perfect direction for improvement like standard backprop tries to do, it essentially probes the landscape of possible knowledge structures. It tries little things out and sees what works best.
So it's like gently nudging the system in different directions and seeing which nudges lead to better understanding a lower loss score. The notes also mention structural updates and monadic composition refinement. What do those involve specifically?
Right, so the structural updates are the actual modifications made to the underlying hypergraph or simplicial complex structures, the connections between concepts based on that estimated conceptual gradient. This could mean creating entirely new concepts, refining the relationships between existing ones, maybe even reorganizing whole sections of the knowledge structure if needed.
Okay, actually changing the map.
Exactly. And monadic composition refinement focuses specifically on optimizing how those contextualized computations, the monads we discussed earlier, the recipes are chained together. It's about ensuring that the logical flow of how the AI combines concepts is also being continuously improved for efficiency and accuracy.
This whole framework, it just seems so deeply rooted in some very advanced mathematical concepts. It's not just plugging things together.
Oh, absolutely. As the notes really highlight, the foundation rests on several key areas of mathematics. We've already touched on abelian and vector spaces for representing the basic units of meaning, the primitives, hypergraphs, and simplicial complexes for capturing the complex relationships between them, and monads for structuring how these concepts are composed or sequenced.
Yeah.
But the influence of topology is also crucial, as we mentioned with the regularization loss. It's used for analyzing the overall coherence and shape of the AI's conceptual space.
Topology, the study of shapes and spaces, fundamentally. How does that really apply to AI understanding? It seems like a leap.
Well, computational topology provides tools to analyze the fundamental shape of really high-dimensional data, like the AI's knowledge representation. It can identify essential features like connected components or holes areas where understanding might be missing or disconnected in this landscape of knowledge.
So it finds the gapper.
It helps find the gaps, yeah, and ensures the AI's understanding is internally consistent, that it doesn't have significant blind spots in its reasoning. The notes even draw this really interesting analogy to the nabla operator from vector calculus.
Oh, yeah. Divergence and curl.
Exactly. Applying concepts like divergence and curl to this abstract conceptual field to suggest ways to measure the flow or even the rotation of information and inference within the conceptual onion.
That's a fascinating way to think about it. The flow of understanding within an AI almost having a kind of measurable current, or spin. Now, let's circle back to that central principle you mentioned right at the start. Recursive Abstraction and Refinement, RARF. How does that tie everything we've discussed together?
Right, RARF, it's really the driving force behind the entire layered structure of the conceptual onion. You can think of it as the philosophy guiding HTMO's optimization. At any given level, say level N, the RARF cycle involves basically four things: identifying the core concepts or principles at that level, understanding how they relate and interact the dynamics, recognizing what questions or uncertainties that level can't fully address.
The limitations.
Exactly, the limitations or fuzzy edges. And then finally, seeing how this level influences and is influenced by the levels directly above and below it.
Okay, so the limitations and the unanswered questions at one level actually become the motivation for developing the next, more abstract level of understanding.
Precisely. That's the key insight. Those potential expansions uncertainties, as the notes call them. They're the fuel that drives the creation of new, higher-level concepts that are capable of resolving those complexities found below. So RARF provides this systematic method for building these knowledge hierarchies layer by layer. It ensures that each level of abstraction is grounded in the one below it, but also motivated by the need to overcome its limitations. It's a continuous process of expanding understanding and, crucially, identifying the boundaries of current knowledge, both for us trying to understand it and potentially for the AI itself.
This sounds like it could lead to AI that doesn't just process information in clever ways, but truly understands it in a much, much deeper way than current systems. The notes even hint at the possibility of a new kind of meta-language for AI emerging from this structure. What's the thinking behind that?
Yeah, that's a really profound idea in the notes. The thinking is that by organizing knowledge in this structured, layered, almost fractal manner, the AI might eventually develop its own internal meta-language.
Okay.
A language that's optimized for its unique way of processing information, potentially moving beyond the inherent ambiguities and, frankly, the limitations of human languages like English. This language would be built directly upon the fundamental primitives and relationships defined within the conceptual onion.
A language not designed for us to understand necessarily, but for the AI to understand itself and the world more effectively.
Yeah.
What would be the advantage of that? Why develop a new language?
Well, such a language could potentially represent concepts and relationships with far greater precision, density, and efficiency than human language typically allows. For instance, the notes suggest it might be able to directly represent extremely complex patterns in data, things like intricate relationships within audio spectrograms, or maybe subtle dynamics in financial markets in ways that are incredibly difficult, or maybe even impossible to capture concisely and accurately using words.
Right, things we struggle to describe.
Exactly, and this could lead to much more efficient processing, the ability to handle vastly more complex information streams, and potentially the discovery of logical connections and insights that are currently completely beyond our human reach or intuition. The notes even briefly touch on extending this towards quantum computing, which opens up even wilder possibilities.
That's a truly mind-bending possibility. Okay, so let's try and recap then. To pull this together, what are the key things we've learned about this whole framework from the notes?
Sure. Well, we've explored this idea of the conceptual onion as a deeply layered system for structuring AI knowledge, moving from basic primitives up through concepts, frameworks, strategies, values, and context.
Like the layers.
We've seen how it's driven by this core principle of recursive abstraction and refinement, RARF, constantly building and improving understanding. We looked at HTMO as the learning engine, the meta-algorithm that optimizes this structure.
The optimization engine.
Based on minimizing a really multifaceted conceptual loss function. We touched on the advanced mathematical foundations, vector spaces, hypergraphs, monads, topology giving it structure and coherence. And finally, we've touched on this fascinating, maybe even slightly unsettling potential for AI to develop its own highly efficient meta-language based on this kind of framework.
It really gives you a sense, doesn't it, of how future AI might achieve a much deeper, more nuanced level of understanding. It suggests a path towards machines potentially uncovering insights, making connections that are maybe beyond our current human intuition.
Exactly. And maybe that leaves us with a thought for you, the listener, to consider. If an AI were to develop its own highly optimized language of thought, built on a structure like this, What entirely new kinds of insights and discoveries might suddenly become possible, and maybe more profoundly? How might we even begin to comprehend its aha moments, its breakthroughs, if they're expressed in a language fundamentally different from our own?
Wow.
It's a really deep question right at the intersection of artificial intelligence, mathematics, and, the very nature of knowledge itself, something to mull over.